in this short video, I just want to discuss a little more detail about oxidation reactions. And one of the things that people often do for helping to remember what is happening during these types of reactions is they have this little acronym where it'll be Leo, the lion says grr, or oil rig. And what they mean here is that Leo is the lion, and it stands for loss of electrons. And that means when something loses electrons, it's an oxidation of that compound. Whenever anything loses electrons, something else always gains electrons. So there's a benefactor and a distributor of the electrons. So the gain of electrons, the thing that is gaining those electrons, is being reduced, and there's a reduction that happens. So these things always happen at the same time. I like Leo the lion says grr better than oil rig, and sorry this got a little cut off, but oil rig, it's the same idea. Oxidation is loss of electrons, reduction is gain of electrons. I don't like this one as much because the electron isn't part of the saying necessarily, the acronym, whereas this one, the acronym has electron in it. So I think Leo the lion says grr is better. But let's look at some examples of this. A lot of different types of substances can be oxidized and reduced. We're going to focus on, in this little part, just on carbon-based compounds. So this is the foundational basis for a lot of things that are happening in organic chemistry and biochemistry. So if we're going to draw the progression of combustion, so combustion is a redox reaction, and I'll show you how that is. So from methane to the most oxidized state of this carbon. So what we can do is we can react this with oxygen. So we are going to add O2, and we can have certain levels of oxidation. So we can have a certain number of carbon to oxygen bonds being formed. We'll first start with just one carbon to oxygen bond. We essentially replace this hydrogen bond with an OH group, which is an alcohol group, and that is one level of oxidation. We can then also create a double bonded oxygen to carbon. That will give us a second carbon to oxygen bond. So this is actually, this second compound is more oxidized than the first. So that may require an addition of some more oxygen. And then we can also finally have another oxidation where we do another oxygen carbon bond where we now still have that double bond here, and then we have another OH bond here. We still would have this hydrogen, and we can do another one actually, O2, and now we can create this carbon double bond, which is carbon dioxide. And so we go from a methane, which is starting here, we go to a methanol and a formic acid, a formaldehyde, then we go to a formic acid, and then we go to the carbon dioxide. So this is a series of redox reactions where we're actually oxidizing the carbon as we move along this chain. We're reducing the O2, and so these things happen at the same time. These redox reactions happen simultaneously, and you can see that we are essentially adding more carbon to oxygen bonds as we move down this chain. And this is very similar to something that happens if we burn methane gas, we'll get carbon dioxide out. And if we eat sugar molecules, they have a lot of carbon to hydrogen bonds that can be replaced with carbon to oxygen bonds, and we breathe out carbon dioxide. It's the same idea, the same kind of thing that's happening, and when this happens, we actually can generate energy from that. The reason that we're actually gaining energy in this system is that when we talk about carbon to hydrogen bonds, there's more of an even sharing between the electrons in here, between carbon and hydrogen, than when we're talking about carbon and oxygen. And it has to do with that internal shell and that shielding, because we're feeling a plus +8 pull on the oxygen versus a +6 pull on the carbon. So the electrons actually get pulled more towards the oxygen in the shared bond. And what that actually means, and this is also a smaller molecule, because we're looking at, if you look at the periodic table, we've discussed this before, as we go from the left to the right, even though we're adding more electrons, those protons are in that same amount of space, and the elements get tinier and smaller. So these electrons, once they get bonded between carbon and hydrogen, they're more equally distanced apart from each other. But once we put the electrons here, they actually get pulled closer to a larger group of positive charge, and that actually provides some energy. It's kind of like a spring. So if you pull a spring far apart from each other and you let go, they're going to kind of zip back, and some energy is going to be released in that movement. And this is what happens with the electrons. When they get closer to that positive charge, they can release some of that energy that was stored in pulling them further away from these groups of electrons. So really, oxidation doesn't have to involve oxygen at all. It can involve hydroxide, for example, but it can also involve chlorine or nitrogen, anything that is more electronegative than carbon, for example, carbon and hydrogen. If we do that, these are all actually oxidation reactions as well. So that concludes this little short video about redox reactions. And the next thing we're going to do is we're going to start to look at how we account for the numbers of things that are chemically reacting. How do we do this in the lab, where if we're going to add a hydroxide or a carbon, we're going to add methanol, we're going to add oxygen. How much oxygen do we know that we need if we have so much methane, for example? How much energy are we going to get out? This can all be accounted for and defined and determined before we even do the chemical reaction. So that's the next step.